true system? That's good. You seem to only have a small select group in the room. Is everyone going on spring vacation?
I believe they may be studying for midterm.
Oh, are they?
They trust the quality of our lecture recordings.
It's okay, that's fair. That's good. We were not scared away by the homework problem.
They don't want to give me that.
Okay.
It's mine something I can do.
So let's start talking about hidden numbers.
Oh, wait a minute.
7. Do we still have questions on homework number 7? Did we get any flutter in homework number 7 as yet? We have flutter. Okay. Okay, you have a question.
Yeah, question.
Okay, what's your question?
My question is, I thought thoughts look like this. And then they convert to hand.
Okay, that can happen.
That is data imaginary.
Yeah, that can happen. Okay, let's share this with the group.
Okay.
This is a plot of the imaginary part of beta versus Q, right?
Yeah. Versus.
And apparently, at least in one case, these two frequencies at Q equals 0, and of course they appear in conjugate pairs. Those are the natural frequencies of the system in the absence of any aerodynamics. And then you're showing that those frequencies coming together at this point. And then the frequencies remain, they are together, and then they eventually go to 0. Yeah. Okay. And now let's look at the real part. You want to plot the real part for us?
My real part looks like this. It's just this.
Yeah. I'll show it to you. Okay. Very fine. Okay. So the real part, I think this actually lines up with this.
Yeah.
Okay. So how do we interpret this? First of all, I think this is probably correct. So you'll be happy to know that, right? Okay. So the two frequencies come together at this point. The real part, because of the simple aerodynamic theory we're using in this particular calculation, remains 0 up to this point, and then one becomes positive and one becomes negative.
Yep.
But the positive one wins in the sense that that is the unstable root, and also it will dominate the motion because it's growing exponentially while this root is decaying exponentially. So if you were to look at a time history, this root would dominate. Now, you're probably concerned about that.
Yes.
Well, this is a linear model. So once it becomes unstable, the rest of this is interesting mathematically, but it has no guarantee to be of any physical significance. Now, if somehow some magic would occur such that you could stabilize the system so that you went up to this point, then I think what would happen is you would now see divergence because this would be 0 frequency, right? Yeah. But in fact, you can't really perform that magic. So once we exceed this value of Q, and this spins it up, near this point, we can use this information to say roughly at what rate the oscillations will grow. But the linear theory says the oscillations will grow forever. And of course, in practice, either one or two things will happen. Either the wing falls off, we exceed the yield stress of the material, or there's some nonlinearity in the wing structure, which will limit the amplitude to some finite value. But to address those issues would require our introducing some nonlinearity into our model. But the linear models really can only tell us what happens up to the point of the first encounter with an instability. Okay? Does that help?
Yeah.
Okay. Yes.
Based on the slide, the real root then bifurcated the second time.
Yes.
It wouldn't matter because it would just be, as you said, kind of just interesting mathematics.
It would be interesting mathematically, but you really can't give any physical significance to it. Having said that, occasionally you will see in the literature, in journal articles, you'll see somebody making a big deal about the secondary bifurcation and trying to interpret it physically. But that, I think, is on very shaky grounds from a logical point of view, because once you become unstable, the linear theory says it's going to forever end. That either means you have a nonlinearity which you've left out, which keeps it bounded, or maybe the system breaks because you feel the use of the material or whatever. You're welcome. You're welcome. Stockholm, do you have any questions about homework number 7?
No, not for now.
Okay, well, that's great. Now, Stockholm, I have another question for you. Is this your last week in this class?
I think so, yes.
Okay. Well, we've enjoyed having you. Next week here in Durham at Duke, we're on spring break, right? Yep. So we're all going to relax. Also, I'm going to be out of town most of the week. Attending a review for one of the Air Force research centers. So what I thought I would do today, since we're at something of a great point, pun intended, I thought I would summarize what I hope you have learned up to this point, and then also give you a preview of coming attractions so you'll come back after the spring break. All right? And again, as I mentioned before, Stockholm, we will not charge you any additional tuition. If you want to continue with the class and do the homework and have all the fun that we will be having here in Durham, on the other hand, I understand that you may have other commitments. And if you cannot take advantage of this very generous offer, we will not be offended. Okay?
All right, thank you.
So today is, good? Yeah. Okay. So here we are. Thank you. Okay. So this is a summary of what we know so far of what we have learned so far, at least what I hope you have learned so far. We talked about static aeroelasticity. Now, static aeroelasticity is a special case of dynamic aeroelasticity, but usually it's addressed as a separate matter for two reasons. One, it's easier for most people to comprehend, and secondly, the mathematical models can be simplified if it really is a static phenomenon. On the other hand, if you do a flutter analysis, and it happens that the divergence did, the dynamic analysis will tell you that. Conversely, if you do a static analysis and flutter occurs before divergence, you'll never know that from the static analysis. So, but nevertheless, we looked at two phenomena. We looked at divergence, which you can think of as flutter at zero frequency. That's one way to think about it. And we also looked at reversal. And when we were doing reversal, by the way, we looked at, say, for example, a wing with a control surface. And we just looked at one wing, but so you won't be entirely of the opinion that this is the only thing that we could have by way of a reversal condition. There's something called rolling reversal, which is in the book, but which we did not discuss explicitly. And in rolling reversal, we look at two ways. So I'm going to think of this as, here's a very thin fuselage. And now there are two wings. And we're thinking of this wing rotating about the fuselage, right? And we have two control surfaces. But this one is rotated up, for example. And this one is rotated down. By the way, if this is rotated down, it rolls this way, right? And vice versa. Well, the same thing can happen here. You can have a case where the moment, the rolling moment, goes to zero. I mean, the reason you have these control surfaces is you want to roll this airplane. And you generally want to roll it at a high rate, particularly if it's a military airplane, you're trying to get out of trouble. And so, if you have a case where the moment, due to the control surface rotation, the rolling moment goes to zero, that's not a good thing. Not a good thing. If you do this case, as described in the book, you have to include the rigid body rolling motion, as well as the elastic deformation of the wing, in and out, right? You have to include all that. So you have a rigid body motion plus elastic deformation. The other thing you should know is sometimes there are control surfaces on the leading edge. The same kind of analysis works out. But why might you want to have control surfaces on the leading edge? Because if you design things properly, if you lose control surface effectiveness from the trailing edge control surfaces, you can still retain some effectiveness from the leading edge and vice versa. In fact, you can program the combination of control surface deflection at the leading edge and trailing edge to give you some more optimal performance. So you should know that all we talked about control surface reversal, and that was fine. That gave you the basic idea. There are other kinds of reversal that people find. Okay, so that's what you learned about static aeroelasticity. What about dynamic aeroelasticity? Well, the two standard problems or phenomena are flutter and gust response. Of course, homework number 7 was a flutter calculation, albeit one that used very simplified aerodynamics. And the rest of the course, just looking ahead to future attractions, the rest of the course is all about systematically looking at unfair dynamic theories, which are more elaborate and more accurate, and generally the ones that are used in practice by industry and even by researchers on occasion. Gust response, again, you can look at various things. You can look at a response to a gust. We didn't talk about it, but there's also the possibility that there could be some aeroelastic effects to maneuvers. Yeah, I'm trying to move this as a rigid body, but even though it's nominally rigid body motion, I'm after the wing is deforming in particular elastically, and there can be aeroelastic effects on the overall performance and motion of this aircraft. And the basic dynamic analysis for maneuvers is similar to, although that for gust, except that in maneuvers, you really are not thinking about random inputs, right? You're thinking about deliberate motion inputs. Okay, so those are the two things. We introduced the idea of random gusts right at the end, and I want to say a little bit more about that. The time ran out for the folks who are in Stockholm, but you in Durham will probably get a little more about random gusts right after the spring break is over. Okay, that's what you learn. Gee, why did it take so long to do that? Homework. Oh, homework. I had to put it on. Okay. Well, if you don't do the homework, then there's a temptation if you just read a book or you just sit in lectures. Well, I understand that. And then you try to do the homework and you say, well, maybe I didn't understand quite as well as I thought it did. That's why we do the homework. It's a sanity check on your confidence and your ability to understand. Okay, so now, gee, that's it. Now let's talk about what happens next. Well, before I get to that, what happens next? Before I get to what happens next, any questions about flutter, gust response, reversal, divergence, ring of light. A couple of things. Someone asked, I think the student asked this, not here today, but someone asked, are we looking at things other than wind? And people do look at other things. For example, the flow through a pipe, a nozzle, right? And this is a very common configuration. And this can also encounter flutter or divergence. Or you could even have some sort of a random fluctuation in the fluid flow, so you would also be interested in a dust analysis. And there's some interesting aspects of that. There's a whole separate subject, a way, I mentioned those two volumes by Professor Fidensis that covers hundreds of papers that have been written about this configuration alone in the context of blood flow, fuel lines, or whatever. One of the most prominent things that comes out of analysis is that what happens in terms of flutter versus divergence depends on the trailing edge support condition. If the trailing edge is free, this will go into flutter. If the trailing edge is fixed so that it cannot move, you might fix this at the other end like this. It can become unstable if it diverges. And for a long time, people agonized about why that is so. And there are some papers on trying to explain this from a Hamilton's principle point of view, which I find less than convincing. And what you can do is you can do the calculation. You find that, sure enough, if this is fixed at this end, it diverges. If it's free at this end, it flutters. And if I put spring supports here, so it's somewhere between fixed and free, there's the magic value of the spring supports where you change from flutter to divergence. So there are lots of subtleties and interesting things depending on the configuration. Okay, but now, Stockholm, do you have any questions about that before I talk about what you're not going to know about unless you come to Durham and take the course next year?
No, no questions.
Okay, so since you may not be here next year, and you won't be with us the rest of this semester, let me spend a few moments telling you what you're going to miss, because really, you're missing the best part of the course. Well, I don't know about that, but you're missing a really good part of the course. So we're going to talk now about unstable dynamics. And this is a high-level overview. First of all, you can study unstable dynamics at different levels of flow models. So, flow models. The highest level usually is thought to be the Navier-Stokes equations. Okay? The Navier-Stokes equations account for everything we know within the framework of the continuum theory of the fluid. They will include viscosity. They will include shock waves, recent shock waves, and it's everything. Even today, it's a challenge to solve these equations numerically, let alone analytically. There are a few analytical solutions, but they're of no value to us, fortunately, for aeroelasticity. So this is still the subject of great effort in the research community. You can also think of the so-called Euler equations, which is no viscosity. So I drop viscosity from the Navier-Stokes equations and I end up with the Euler equation. And then you can develop what is usually called small perturbation theory. Small perturbation theory means the following. I assume that I have an airfoil, I have a flow, and this is a highly streamlined shape, so it doesn't change the mean flow very much. And any motions are small. How small? Small, well, it depends on the Mach number and lots of other things. So we're talking about a few degrees in angle of attack, typically. If you were in a low-speed flow, you might get as high as 10 degrees and still be in the small perturbation range. At Mach 0.8, you might have to be less than 2 degrees to be in the small perturbation range. On the other hand, remember, in flutter analysis, you're interested in the onset of the instability. So by definition, within the framework of the linear model, you're looking at small motions, which are going to grow to big motions, but you're only interested in knowing whether the motions are going to grow or decay from linear flutter analysis. You're not after how big they eventually get. So small perturbation theory is the heart of most aeroelastic analysis in industry today, and even in research efforts often. So what does that allow us to do? Well, that allows us to do the following. If I think of having a set of flow velocities, which I'll call U, V, and W, these are the three components of the flow velocity in a three-dimensional fluid. And what I'm going to do is I'm going to assume that U, which is the flow velocity in the mean flow direction, is the mean flow velocity, whatever that is, plus U hat. And this, by definition, is independent of time. And this may depend on time. It may depend on the three spatial variables, x, y, z, and time. This one is usually thought to be just a plain old constant, although if you're using the Navier-Stokes equations, this would be also a function of x, y, and z. But in the classical theory, it's usually just taken as that mean flow velocity. And then you assume that v and w, the components in the other two directions, they're also, in some sense, perturbations. And so what you're assuming in small perturbation theory is that U hat, V hat, W hat are all much less than U. If I do that, that means I can linearize the equations in terms of these perturbations. Formally, if I do that for the Euler equations, I get something which still I can do that for the Euler equation. Okay. But then there's a logic that leads to the fact that if these perturbations are really small, then you can introduce the idea of a so-called velocity potential and deal with potential flow. That also means you can assume that the fluid is isentropic, which means there's an inequality between pressure and density. And you can do all sorts of interesting and clever things mathematically for potential flow. So there really is a distinction between potential flow and Euler equation flows. But if within the small perturbation assumption, they're essentially equivalent. So we're going to look at inviscid flows. We're not going to look at the Navier-Stokes equation, at least not until we get toward the end and I run out of other things to talk about. But probably not going to happen. So we're going to look at inviscid flows, and for the most part, we're going to look at potential flows. And the potential flow means the following. If I think of Q bar, a vector, fluid velocity, never, ever to be confused with dynamic pressure, and never, ever to be confused with the generalized coordinate in Lagrange's equation. Because this is the symbol that people use. If I assume that this is U I hat plus V J hat plus W K hat, where I, J, and K are unit vectors in the respective directions, X, Y, and Z, then the nature of potential flow theory is that we assume that Q hat can be derived or defined as the gradient of some scalar potential. Okay, this is the velocity potential. A potential is something when you take the gradient of it, I get something I like it, and I'm interested in, namely flow velocity. Yeah. So for the most part, we're going to be looking at potential flow theory. And if you assume small perturbations, really small perturbations in potential flow theory, this velocity potential satisfies a certain partial difference equation, which turns out to be the wave equation. So when you took that course in PDE, and you talked about Laplace's equation, and the wave equation, and the heat conduction equation, one of the reasons you did that is when you started your study of unstable dynamics, it would all be helpful. So the wave equation is the Laplacian of the velocity potential minus 1 over a wave speed, which will be the speed of sound in the fluid, times the second derivative of the velocity potential with respect to time, equals 0. Those TT are mean derivative of the velocity potential with respect to time. Okay? So we're going to be looking at the wave equation. If in some sense the speed of sound is large enough, strictly speaking, it's the Mach number has to be large enough, then I can throw away that term. So for low speed flows, low Mach number flows, the wave equation reduces to the Laplace equation. And if I'm near Mach 1, this small perturbation idea has some difficulties. So I'm not going to tell you all about that today. I will just tell you that if we're at Mach numbers sufficiently high compared to 1, this is a good approximation for real airplane. If the Mach number is less than 1, sufficiently less than 1 is a good approximation. If I'm in the Mach number range roughly from 0.8 up to 1.2, which is critical for aeroelasticity, this theory becomes more questionable. And that's why people are still doing a lot of work on transonic flow, because you need to improve on this. There is a nonlinear version of the wave equation which attempts to give you something that's useful in the Mach number range between 0.8 and 1.2. And depending on which expert you talk to, they will say that's not too bad or yes, terrible. The ones who think are terrible are the ones who are trying to tell you there's heat and peak. The ones who think it's good enough are the ones who have a potential flow code, and they want you to believe that they know how to correct it. Mach numbers, you know. And there's something to be said on both sides of that debate. Okay. So now the wave equation as I've written it is the correct equation for the velocity potential. If I'm sitting stationary in the flow and the airflow is passing by. Okay? And therefore, in fact, an analytical solution is known as the wave equation. A general analytical solution. The trouble with that analytical solution is it's hard to apply the boundary conditions. Right? And it's hard for a number of reasons, but one reason is it's much easier to apply the boundary conditions on the wing if I'm in a coordinate system that's fixed with respect to the wing rather than fixed with respect to the flow. But if I do that, if I sit on the wing and let the flow move by me, if I'm in that coordinate system, then this wave equation has some additional terms. Rather than having PTT, rather than having the second derivative, thank you, the second derivative of c with respect to time, in the new coordinate system, it becomes, well, it's usually referred to in this fashion, where d is an operator, which is the partial with respect to t plus u times the partial with respect to x. This additional term is what allows me to move from one coordinate system to the other in a small perturbation. So, the final equation then, that we're going to be dealing with, I now will write it out in its full glory, is I'll have phi xx plus phi yy plus phi zz. That's the Laplacian operating on the large potential, where these x, y, and z's indicate derivatives with respect to those variables. Minus 1 over a infinity squared times phi tt plus 2 u infinity phi xt plus u infinity squared phi xx. All of that is equal to 0. Where this is that second derivative convection operator expanded out in this full derivative. And now if we look at the special case of, if you will, statics, as we're going to set time derivatives to 0. Then this would become pxx plus phyy plus pzz minus u infinity squared over a infinity squared times pxx equals 0. Okay?
Yeah, u infinity is an h power in all three dimensions of this.
In the x direction. Yeah, because that's what I said. And whichever direction that u infinity is in, by definition, I call that the x-axis. And then the y and z axis are perpendicular to the x-axis, right? So I set things up that way. Yeah. But here's the thing. You see, I have two terms involving pxx, which I can combine. One minus, now I'm going to introduce the idea of a Mach number, times pxx plus phyy plus pzz equals 0. Whereas the Mach number, by definition, is u infinity over a infinity. Okay. Clearly, this term changes sign depending on whether a Mach number greater than or less than 1. If the Mach number is less than 1, then this has a positive sign. And you can rescale everything. Maybe you know this, maybe you don't, but you can rescale everything. So this just becomes a positive. So if you have steady flow and you're in subside flow, if you have a solution for Mach number 0, you can just rescale it so it's a solution for some other Mach. For steady flow, not for unsteady flow, but for steady flow. This is a well-known classical result. On the other hand, if the Mach number is greater than 1, then this sign, the sign of this coefficient becomes negative. Well, if I have a negative sign here and positive sign here, this is, in fact, even in steady flow, a wave equation where x is a time-like variable from a mathematical point of view. Okay. So even in steady flow, you have this distinction between the Laplacian equation for subside flow and the wave equation for superside flow. When you have unsteady equations, when I put the time derivatives back in, it turns out that for any Mach number other than 0, you have both wave-like properties and Laplace-like properties, whether you're at any Mach number, less than or greater than 1. And then it turns out, perhaps not too surprising, right at Mach 1, you make a transition from so-called elliptical or Laplace-like behavior to wave-like or hyperbolic behavior. In fact, it's elliptical. It looks sort of like the heat convection equation, although it's not really heat convection. But if you're in the Transonic regime, there's a more appropriate equation, not terribly accurate, unfortunately, which is a transition between elliptical to hyperbolic behavior, or between Laplace to wave equation-like behavior. Okay. It turns out, perhaps not surprisingly, that supersonic flow is easier to deal with. It's easier to work with the wave equation than the Laplace equation. I don't know if you found that to be true when you took your PDE course or not, but I think it is. And the reason is because the wave-like variable, in this case x, in supersonic flow, has that time-like quality. Namely, if I have an airfoil and I have a flow over it, and the Mach number is greater than 1, it's easy to show mathematically, but it's also been verified experimentally, that basically nothing ahead of the airfoil is disturbed. The flow is completely undisturbed ahead of the airfoil. That means if an airplane is flying toward you supersonically, you don't hear it until it's gone past. Then you're probably going to hear it a lot because it probably has a sonic boom. But until it passes you, you don't hear it. There's a shock wave that goes down and goes up, and you're here, right? You don't hear this until the shock wave passes. So that makes our life somewhat easier because I know what's happening up here, namely nothing. Conversely, if I'm back here and I disturb the flow back here, it can't catch up and get onto the airfield. So basically, it's particularly a 2D flow, right? I don't have to worry about the third dimension. I just need to look at what's happening in the region from the leading edge to the trailing edge. And I don't need to think about what's happening ahead of the airflow or behind the airflow. So we're going to look at 2D supersonic flow first because of that physical and also mathematical. So the plan of attack then is 2D supersonic flow. We'll do that. Then we'll do 3D supersonic flow, but still has some of that same variable because again, there's nothing happening ahead of the leading edge of the wing if it's flying supersonically. Then we'll do 3D subsonic flow. And then we'll talk about what happens when the Mach number is in the range of 1. And when we develop our solutions, we'll see that in 2D supersonic flow, everything breaks down if the frequency of the oscillation goes to 0. That is, the classical supersonic 2D theory breaks down in Mach 1. Actually, the classical 2D subsonic theory also breaks down in Mach 1. In unsteady flow, if the airflow is oscillating rapidly enough, you can still get a sensible answer out of the small perturbation analysis. Okay. Even if Mach 1. But it has to oscillate more and more rapidly, it turns out. And you get a sensible answer as you get closer and closer. And that should take us through the rest of the semester. Yes. Well, we can. Well, within the framework of small perturbation theory, hypersonic is not different from supersonic. What happens in the hypersonic flow is that the bodies have to be really slender to use small perturbation theory. There is something called piston theory, which is very popular among aeroelasticists. And there are several versions of piston theory. In fact, Kevin McHugh, as part of his PhD thesis, I think about that. The classical version is a linear theory, and it's no different for Mach 2 than it is for Mach 10. There's a nonlinear version of piston theory, which allows you to use it at higher Mach numbers and account for the shape of the body and its interaction with motion. And we can talk about that, particularly since Kevin is nice. I kind of been Kevin in to give it lunch. That was a likewise. Yeah. Yeah. So remind me, and we can do that. We can do that. Yeah. So there is a that would be that's interesting because the non-linears become important in transite flow, and then they become important again as the Mach number increases. In fact, let's assume I have a symmetric airfoil just for fun. And let's say the maximum thickness is, what do you want to call the maximum thickness? Max T. Well, let's just say maximum thickness. normalize it by the chord. Okay. And what is known is that when the Mach number times the ratio of thickness over chord exceeds 1, this is sometimes called the hypersonic regime. The classical linear theory breaks down. So, this might be 0.05 with the thickness ratio, and therefore you want that to be on the order of 1. That means if you're at Mach 20, you're hypersonic. If this were a thickness ratio of 0.10. But even before you get to that region, we'll probably see some nonlinear effect, right? So sometimes I wonder if you'll think people say anything above Mach 5 is hypersonic. Well, it depends on the thickness rate. It really does. It depends on the type of body you have. It's not just the Mach. It's a combination of the geometry and the Mach. Okay. What else do I want to tell you? Well, I think that's really all I want to tell you by way of a preview. If I said more than that, we'd really get into the details. So I'm going to wait till after the break to start our 2D soup side discussion. One thing we didn't do, but maybe I could give you a hint on that. Remember, for the most part, in our course up to this point, we looked at this relatively simple shape, and we, in our Claire analysis, we looked at what I'll call a beam rod formulation, where we're bending the elastic axis and rotation about it. Well, if you get the superside flow, you might have a delta wing like this, right? This really behaves more like a plate. A beam model, even with both torsion and bending, is not enough. You need a plate model. And I think I briefly wrote down what the plate theory would look like. But basically, you're now dealing with some deflection out of the plane, which depends on x, y, and of course time. And now you need a potential energy expression that is written in terms of W. But we know, once you write it down, it's 1/2 the double integral of something called d wxx plus wyy. I probably will almost remember the other terms. 2, 1 minus nu, I think, wxy squared plus wxx times wyy. That's accurate to within a factor of coefficient, right? But the point I want to make to you is that if I take wxx, xy, and t, and I express it as summation over m of, I'll call a sub m of t, times some cleverly chosen functions x and y, I can reduce this to a quadratic form in terms of the a's and use Lagrange's equations and be on my merry way. So all I really need to do plate theory is I need someone to tell me what those functions are. That's why I have a finite element code. Because the finite element code will compute the natural frequency of all the same structure of centers. And once I have the natural frequencies, I can also compute the natural modes. I'm going to use those here, and then Lagrange's equation, that way I go. And then for the virtual work, kinetic energy is just going to be 1/2 the double sum of mass w dot squared dx dy. Where w is the deflection, w dot is the velocity. Again, I expand in terms of motion. And then virtual work is just going to be the double integral of the force per unit area, otherwise known as the pressure, which is going to come from my aerodynamic theory, times del of w, right? The virtual change in W, dx dy. And again, with my mole expansion, I'm home free, provided I know P. But that's why we're going to study unfavored dynamics for the rest of the semester. So, although we have a simpler structural model, we can do plate. Or we could do a plate which is stiffened by beams, and we do all the same thing. Right? As long as I can write down potential energy, kinetic energy, virtual work, I'm good. Yes.
I have a question, which is kind of related, but when you design a profile, okay, for example, wing and so on, do you take into account the phenomena, and if so, how do you design the profile? Take into account that.
Within the classical theory, the profile does not influence the flutter speed or the test response or anything else. Okay. Those are higher order effects. And so there would have to be some sort of nonlinearity in the system. For example, if I have a plate and I have a certain profile, that profile will create a static pressure difference across the way, right? That will load that plate. That plate will deform. If that plate deforms, assuming it's a cantilever plate, it would have to deform on the order of somewhere between 10 and 20% of, say, the wingspan before I would be in the nonlinear range of that structure. But if you look something like the 787, the 787, you put that there. And then the profile would have to be taken into account. Okay. That would have to be taken into account. And I presume they tried to do that. But the classical theory, the classical linear theory isn't important.
And what's the idea of thinking that is about? Like,
well, yeah. Well, the simplest thing to do would be to call the natural frequencies of that wing would change as the static friction gets in that range. So you would have different mode shapes and different natural frequencies of that structure. Okay. But you can still think of a small perturbation, small dynamic perturbation about that large statically deformed structure. Well, that's one thing. And that's relatively straightforward. People pretty much know how to do that. And even within the frame of our course, you can just think of it as a new set of modes, a new set of natural frequencies for the structure. But now there's the varies depending on the static loading. So you would have to, if you're a flutter engineer, you'd have to think about what static deformation condition is most critical for flutter. You would presumably want to determine the flutter speed as a function of the amount of static loading. The way airplanes are designed, having said that, there's a lot of static deformation when you're on the ground due to gravity. But they're usually designed so that the gravity and the cruise condition combination is such that the wing, when it's implied, looks pretty straight. So the first thing to do is just ignore the work altogether. But if you really wanted to think about it, you know how to quantify the structural amount. Then the question is that deflection, 10 to 20% reflection compared to the span, is that enough that I have to think about the aerodynamic nonlinearity? And it might be, because if I cruise at Mach 8, I'm getting close enough to Mach 1. That kind of deformation might take me into a range where that would be important. And so people have tried to, and still do try to modify the classical potential flow, usually by filling out the coefficients and inflections to account for the static, what I'll call the static nonlinearity. They're still thinking about a small dynamic perturbation about some mean flow, but now we're thinking that the mean flow near the wing is no longer just a constant u, but there's a variation in the static velocity field over that wing because it's deformed to a certain degree. Or they might try to run a CFD code. In my opinion, there's not much point in running an Euler code, so I don't think you get an answer much different from the potential flow code. But you might be concerned about the viscosity and the interaction of the shock waves and all that. More likely, they'll just use the classical methods, and then if they Can you have enough margin of water velocity, for example? They'll go to a wind tunnel test program. And then if they still don't think they have enough margin, they'll do a very careful flight test. Or they might go back and redesign the structure and split them up so they can have more margin. Does that help? Yeah. But there are methods out there that will allow for the influence of the shape of the wing and also for the static deformation of the wing under static airborne influence and its impact on the sun. Well, that takes you to a more frontal.
So field that doesn't apply to take off conditions. Like the 787, you take off at very huge standing up the wings.
Yeah, of course that's not a flutter critical condition, right? So, yeah, and they're relatively low speed. I'm not working for Boeing or Airbus, I can't be sure. I wouldn't think they have to worry about that in terms of the performance and the overall physical body motion. I think from an aeroelastic perspective that would not be a condition they would worry about very much.
I think there's something about the problem that handling actual surfaces that actually that you put like a completely different element, different piece of material on the wing. It's not actually going to follow the reflection of the wing. So actually you need to have some correction factor for that, especially if you take off. Because like the whole wing like deformates continuously, but the console surface is not that the deformation of the wing during takeoff.
Yeah, but what are their concerns? Are they just worried about the structural integrity of the wing?
No, also like kind of like reversal or stuff like that. Because like at that point, it's like the geometry of the wing changes, but the geometry of the console surface doesn't change.
Yeah.
So you actually got take into account that for reversal conditions.
Well, when the plane comes in for a landing, the typical airline comes in for a landing, the wing comes apart, right? You've got all these control surfaces under the wing, and that flow is pretty ugly. But what they're trying to do is really drag, because they want to slow down the airplane. Right? They want to slow down the airplane, but they also want to have enough lift that they don't hit the runway too suddenly. Well, they want to have a gentle landing. Yeah. But I don't think that structural integrity per se is an issue. Therefore, I don't think aeroelasticity is an issue. But someone's worried about all this phenomena. Absolutely. Okay. I think I'm going to stop here. Is that right? No. And you're going to have a happy holiday for the next week? Oh. Telephone, do you have any questions before you do whatever you do over there?
Will there be any discussion on homework number 7? Correct?
Sorry, say again?
Will you discuss the result homework number 7 after the spring break, or
What do you want me to homework number 7?
The one you start with the solution.
Oh, I don't have them yet, but I'd be happy to. You want to come by in a week's time and hear about that?
Well, I'm just curious about the answer, the correct answer.
Okay. What we will do is we'll post an official solution for homework number 7, so you'll have that to look at. Okay.
And we're also going to continue posting recorded lectures on Sakai. So I believe you'll still have access to those.
Yeah.
Okay.
And I will discuss homework number 7 when we come back from our spring break.
Okay.
Okay?
Yeah. Thank you.
All right.